Just like with vectors, we have certain operations we can perform on matrices. Let's look at some of those now. So first, there's matrix addition. To add two matrices, first off, the two matrices have to have the same number of rows and columns. So for example, if we have the matrix 1, 2, 3, 4, 5, 6, and we're adding to this the matrix 7, 8, 9, 10, 11, 12, this is not defined. The two matrices don't have the same number of rows or the same number of columns, so we can't do this addition. So that problem actually doesn't make any sense. Despite the fact that they both have 6 entries, we don't define addition in this case. However, if we've got 1, 2, 3, 4, 5, 6, plus, and the other matrix has the same number of rows and columns, say 7, 8, 9, 10, 11, 12. Now these two we can add together, and we add these component-wise. So this matrix has 2 rows and 3 columns. It's a 2 by 3 matrix. This has 2 rows and 3 columns. So the answer, the sum of these two has to have 2 rows and 3 columns. So in the first row, we add up each entry. So 1 plus 7 gives us 8. The next entry, 2 plus 8, gives us 10. The next entry, 3 plus 9, is 12. Then we go to the lower left corner. 4 plus 10 is 14. 5 plus 11 is 16. 6 plus 12 is 18. So we add 2 matrices that have the same number of rows and columns, and we just add component-wise. So that's akin to vector addition, that we can only add vectors of the same dimension. Now we also have the idea of scalar multiplication. And this, just like with vectors, we can take any matrix, say 1, 2, 3, 4, 5, 6, and multiply this by any scalar, and you can think of that scalar as distributing to every component of the matrix. So we distribute along the first row, so negative 2, negative 4, negative 6, and then distribute along the second row, negative 8, negative 10, negative 12. So scalar multiplication works for matrices just like it does with vectors. And finally, we've got the idea of matrix multiplication. Now this is a little bit weird. First off, in order to be able to multiply two matrices, if we take a matrix A, which has some number of rows and some number of columns, and we try to multiply it by matrix B, which has some number of rows and some number of columns, for reasons that will become apparent in a minute, we only define multiplication if the number of columns in the first matrix is the same as the number of rows in the second matrix. Otherwise, the matrix multiplication isn't defined. So let's look at a fairly small case. Let's look at a 2 by 2. Let's say we have got 1, 2, 3, 4. So this is a 2 by 2 matrix, 2 rows, 2 columns. And we're going to multiply this by, say, 1, negative 2, negative 3, 4. This is also a 2 by 2. So the number of columns here matches the number of rows. So it works, so I know I can do the multiplication. Now to actually do this, to get the, so let me just label this as row 1, row 2. This is column 1, column 2. To get the entry in row 1, column 1, what we do is we take row 1 of the first matrix and we dot product it with column 1 in the second matrix. So to get the row 1, column 1 entry, we dot product row 1 and column 1. So 1 times 1 is 1. Let me actually write this out. And then 2 times negative 3 is negative 6. So we multiply and add those together, we get negative 5. To get the next spot, to get the entry that's in the first row, second column, we dot product the first row with the second column. So we take 1, 2, and we dot it with negative 2, 4. So 1 times negative 2 is negative 2, plus 2 times 4 is 8. Negative 2 plus 8 is negative 6. Positive 6, excuse me. So now we look at the bottom row. So to get the entry in this corner in row 2, column 1, we dot product row 2 with column 1. So 3 times 1 is 3, plus 4 times negative 3 is negative 12. 3 plus negative 12 is negative 9. Now to get the last entry in here, it's in row 2, column 2. So we dot product row 2 with column 2. So 3 times negative 2 is negative 6, plus 16 is 10. So that's the answer we get from that matrix multiplication. It's kind of a quirky definition. Let's just go and verify why this has to be true. Let's say that they didn't have the same number of, the number of columns here wasn't the same as the number of rows. Let's take the same example, 1, 2, 3, 4. So this is a 2 by 2, 2 rows, 2 columns. And I'm going to multiply this by a matrix which has maybe more rows. So let's say this one has 3 rows and 2 columns. So let's make this 1, 2, 3, 4, 5, 6. So this has 3 rows now and 2 columns. So I see that these inner dimensions don't match. So let's see why this doesn't work. Okay, so first off, to get the entry in the first row, first column, I'd have to take the first row and dot product it with the first column. Now I can't do that because the dimensions don't match up. I can't dot product 1, 2 with 1, 3, 5. So that means this multiplication actually doesn't make any sense because I can't dot those together, so I can't get any of the components to match up right. So for matrix multiplication, it's not that they have to have the same dimensions, it's that they have to have the same inner dimensions. Let's look at a more beefy example just to make sure everyone's got this. Let's say we take the matrix 1, negative 2, 4, 3, 1, negative 6. So this matrix has 2 rows, 3 columns, and let's multiply this by a 3 by 2. Let's say we've got 2, negative 1, 3, 2, minus 1, 4. So this has 3 rows and 2 columns. So to figure out first off the dimension of the product here, so I know that these are the same, and we'll wind up dot producting those two, and those dimensions sort of cancel each other out. So the only dimensions that are left over are 2 by 2. So my answer should be a 2 by 2 matrix. Let's just go through and do that. So here's row 1, row 2, column 1, column 2. Here's row 1, row 2, column 1, column 2. So in order to get the row 1, column 1 entry, I take row 1 and I dot it with column 1. So what we've got here is 1 times 2. So that gives us 2. Plus negative 6. Plus 4 times 1 is negative 4. So that's giving us negative 8 when we multiply those two together. Okay, so now let's look at the next entry. This is row 1, column 2. So we'll take row 1 and we'll dot it with column 2. So we take the dot product of these two. We've got 1 times negative 1, negative 1. Negative 2 times 2 is negative 4. 4 times 4 is 16. We dot those together and we get, looks like 11. Okay, now let's look at the second row. For the second row, we're going to take row 2, and since we're looking at row 2, column 1, we'll dot it with column 1. So if we dot these two together, we get 3 times 2 is 6, plus 1 times 3 is 3, plus 6 times, negative 6 times negative 1 is 6, which gives us 15. And then in this last entry, this is the second row, second column, so we'll dot product the second row with the second column. Now we multiply these together. We multiply the first coordinates. 3 times negative 1 is negative 3. We multiply the next ones. 1 times 2 is 2. And multiply the last two. Negative 6 times 4 is negative 24. This gives us, looks like negative 25. So we multiplied a 2 by 3 and a 3 by 2 and wind up getting a 2 by 2 matrix. So multiplication is a little tricky, but those are the quick overview of the operations for matrices.